Welcome to ME 571, Reliability in Engineering Design. My name is Ganesh Subbarayan. I'm a professor of mechanical engineering at Purdue University. It's going to be my pleasure to teach you reliability concepts and how they can be used to influence design. This is the first module. I'm going to be teaching this class in modules and submodules. So broad topical modules, then subdivided further into submodules. And I'll start with description and procedures, overall outline of the course. So we'll start with course objectives. What can you hope to get out of this class? You can hope to learn methods of reliability analysis, understand the importance of reliability as well as quality in design. In other words, how to influence the reliability of your product during the design phase, and learn to apply to design of mechanical and electronic system, to a less extent design, but more to understand reliability of electronic systems. What are the common modes of failure and how design might influence the occurrence of those failures. So those are broadly the course objectives. The course will utilize concepts that you might have learned in an undergraduate mechanical engineering design course. And if you haven't had that background, you can pick it up, but you should let me know. Some of the concepts that we will use are things like shear force and bending moment diagrams, notion of stress and strain, principal stresses, principal strains, and static failure theories. The reason why we need them is because what we are learning is influencing the reliability of a product at the design stage, and design of any mechanical system requires an ability to analyze stresses and strain, because that's what we want to design to improve. We want to prevent failure due to excessive stress, and that's the reason why we would need to have this background. The textbook and reference material that we will use, and we would use them alongside other material. So the textbook is McPherson, Reliability, Physics and Engineering, Time to Failure Modeling. The references that we will use are posted PowerPoint notes. The PowerPoint notes would be the primary reference, and we would also use as a secondary reference Practical Reliability Engineering by O'Connor. The topics that we will cover over the course of 15 weeks of lectures is the first week I will introduce you to the topic of reliability. And since reliability requires an understanding of probability and statistics, we'll start with rules of probability. In the second week, we'll continue on with probability examples and conditional probability, discussion of conditional probability. In week 3, we'll discuss expectation and variance. Since reliability is concerned with characterizing uncertainty in failure times, and failure times are often complex functions of design parameters, we need to be able to understand what the uncertainty in an output, in a general output function performance metric will be given uncertainty in the individual design parameters that we try to influence during design phase. So we need to understand expectation, which is a measure of central tendency, measure of where you would expect on most occasions a particular parameter or function to be, and variance, which is a measure of how that value is dispersed or spread. So we would learn how to characterize expectation and variance of not just individual random variables, but also of continuous functions of random variables. Then we will go on to discuss various common probability distributions such as normal distribution. We'll start with normal distribution. We will introduce the notion of probability density function and cumulative distribution function. And then in week 4, we will do the first engineering application, first introduction to probabilistic design through something called load strength interference theory. So far, in our undergraduate, we have learned deterministic design, that is, where we think of strength as one number and we think of load as one number, and we account for the uncertainty in strength of a material, meaning that strength is always not one precise number, but it has a range. And we account for the uncertainty in load through a safety factor. So here we will learn to not design through safety factors, but design probabilistically to achieve a prescribed number of failures or max number of failures that we will allow. And that theory is the load strength interference theory. And then in week 5, again, we'll continue with an engineering application. We'll understand material degradation, meaning that all systems, the performance of systems will degrade due to strength of the material being degrading. And we will learn how to characterize that. And then in week 6, we'll talk about log normal distribution. We'll first define reliability. We'll define hazard rate, mean time to failure, mean time between failures, availability, and so on. Then in week 7, we will learn about exponential distribution and ways to estimate mean time to failure. Then we will go on to discuss Weibull distribution, data fits, failure rate modeling. And in week 8, we'll talk about complex failure mechanisms where you might have multiple failure mechanisms, those that might be clearly separated and those that might not be clearly separated, meaning those that might have mixed multiple failure mechanisms, how to go about fitting data to those kinds of failure phenomena. Then we will then assess how good our fits are, whether our assumed distribution, whether it's Weibull or log normal, how good that fit is. Then we will talk about decision making through binomial and Poisson distributions, where we will ask the question, if given a certain component level failure, we will learn how to make decisions based on that component failure distribution as characterized by log normal, Weibull, exponential, or normal distribution. So we will begin our introduction to system level reliability. We'll continue that in week 10 through reliability block diagrams, and then in week 11 through Monte Carlo simulation. And then we will begin our discussion of mechanical systems and failure in mechanical systems. We'll talk about how uncertainty in performance metrics in mechanical systems comes about due to uncertainty in geometry or load or strength. And then we will learn about the statistical concepts of covariance and correlation. And then in week 12, we will learn an alternative technique to Monte Carlo simulation called first-order reliability methods. Monte Carlo simulations we will learn to be very expensive, so the alternative is an approximation that allows us to estimate uncertainty in complex nonlinear functions much more efficiently. And then we will learn other concepts such as failure modes, effects, criticality analysis, fault tree diagram, etc. in week 13. And then in week 14, we'll go on to talk about accelerating the failure. So we can do, in lab environments, we can accelerate failure and estimate what the life would be in field use, because oftentimes we don't want to wait for a real product to fail while developing a product. So what we would like to do is to subject the product to a more aggressive condition so it causes the product to fail sooner than it would in real life, and thereby estimate what the life of the product would be. We will learn to do that in week 14. And then finally, we will, in week 15, we will look at time to failure models for mechanical systems and also, to an extent, electronic hardware as well, in as much as the failure mechanisms are very similar to mechanical systems.